We left off the other day on page 232 of your packets. We had done the top part of the page, which is what I have up here. Remember that when you get a negative number for doing b squared minus 4ac, when you do the whole quadratic formula, you're going to have a square root of negative, which creates our imaginary answer. So they're going to be roots that don't exist. And what happens here is that as you're graphing your function, even though it is to the fourth power or something like that in our next problem here, not all of them might cross the x-axis. Some of the roots, even if you have a fourth power answer, it may not cross 4 times or have the multiplicities add up to 4. Some of them may be imaginary that you have less, but you still have the total that works through with all of them when you're working with that. So whatever the power is on your problem, so for example, on this guy here that we're going to look at in a second, if you have something to the fourth power, the total of your positive roots, your negative roots, your zeros that you have when you get like an x squared out front and you get that x equals 0, how many you have of those, and your imaginaries has to all add up to 4. So if you look at this problem here, when I look at my table, going across, they all have to add up to equal 4 all the time. And we'll talk about that more in a minute. So on this, we had gotten our imaginary roots working it out that we've already done. So let's look at the bottom half of the page. We have this function here where it is to fourth power, so it's quartic, and they're asking us how many imaginary roots we can have. Now, imaginary roots always come in pairs, because when you take the square root of something, you always have the plus and the minus version of it, that it comes together. So if you have something to an even power, you would start with that power, and it could go down in pairs of 2 from there. So it would go from 4 down to 2 down to 0. Now, if you have something that has an x to the third power, for example, okay, do not start with 3 for the number of imaginary roots you can have, because remember, they only come in pairs. So you can have 0, you can have 2, you can have 4, and so on up. But if you have an x to the third, the most that you could have for imaginary roots would be 2. Because the maximum number of total roots you can have are 3, so at most you could have is 1 pair of imaginary roots, because they always come in pairs as you're working through it. Now, with Descartes' rule of signs that we covered on the first part of this section, you look at how many sign changes there are for the original function that you're given. So when I look at this one here, we start with a positive, and then we move to still being positive. Then here finally it switches to a negative. And then from the negative here, it switches back to a positive, and then it stays positive. So with this here, I have 2 sign changes. So the maximum number of positive roots that I can have are 2. Or if I had an imaginary pair, it could go down to 0. So if I had an imaginary pair, that kind of takes away from that. So I have 2 or 0 are the possible options of what could happen with my positive roots. When I check out f of negative x, well, I plug negative x back into the function, and wherever it is even, like to this fourth power here, that term really isn't going to change, because a negative x to an even power is just going to go back to being positive and not change anything that's happening there. But when I plug in negative x to the third power, it stays negative. And then when I plug in negative x here, it's squared, that part goes back to being positive, and then the negative 8 does not change there. And then when I plug in negative x here, it changes it to a negative 2. And then, of course, the 3 doesn't have an x, so it's not going to change. So basically, what happens between my things here as I'm working with it is wherever there is even powers, it stays the same as it was. But wherever there's an odd power, it's going to change signs. So this changed to a negative from where it was a positive up before. This stayed negative. This changed to be a negative, and this stays. When I look at this now, I start positive, I switch to being negative, and then I stay negative for a bunch of them, but then finally we switch back to being positive for the 3 on the end. So here again we have 2 sign changes. So you can have 2 or 0 for possible negative roots. That's our options of what could possibly happen. With this problem, no x's are factored out because we have a constant term on the end. So there isn't like all the terms have so many x's with it that I just factor an x out to start my problem off right away. So because of that, I don't have any roots where just you have x equals 0, because you have like an x squared out front or an x where you factor the whole thing out. So I don't have any of those here. So when I come to my table here, this column is always going to stay 0. Then when it comes to the imaginary roots, I have a possibility of having a max of 4 or 2 or 0. Just I have to kind of play around with that so that I can complete my combination of positive, negatives, and zeros so we get our total of 4s going on across there. So then it's a matter of playing around with this and coming up with all the different options of what could happen. So you make a table. And I like to start, and they also did here, with the maximum number of positives. So I could have 2 positives, and then they also maxed out the number of negatives, which would be 2. Well, if I do that, I've already used up my 4, so I have to not have any zeros here because we talked about that over here. But then this is also going to be 0 for this also, and that would give me my total of 4. I did 2, they did 2 again here on the positive, but now they switched it to being 0 on the negative. With that happening, now we can do 2 imaginaries. Or we could have 0 positive, you could have 0 negative, and everything could be imaginary. Or you could have 0 positive, have 2 negative, and have 2 imaginaries. Those are our 4 different options of what could happen. Now the directions tell us that we're supposed to go back and graph the function on our calculator and put a star by the combination that is correct. So you can see here that they've starred this one, and the reason why is... Oops, let's see if I can get my page changed here. Here is the graph that goes with this function. So if you were to take your graphic calculator and do that, let me clear these annotations out of the way. Here is the graph. As you can see here, we have a negative root here, a negative root here. So we have 2 negatives. We don't have a 0 root. Then it almost looks like it's tangent, but if you can look in closely there, it dips slightly underneath there. So there is 2 positive roots also. So the correct answer was the top line. That's the one that actually happened. These are all the different options of what could happen. Only one of them is actually going to happen as you go through it. At this point, I want you guys to pause the video, and I want you guys to work on the next page, 233, and you can work in groups of 2 or 3, and work on doing your sign changes for when it's just f of x. Then do f of negative x and figure out how many sign changes you have. So figure out how many possible positive roots could you have. Remember, they can go down in groups of 2. And then how many negative roots could you have, and they can go down in groups of 2 also. Look for if you have any zeros, if you can factor an x out of everything to figure out how many 0 roots you have. And then look at the total power to kind of decide how many imaginary you could have, and then work on making a table that you have with it, okay? After you've done that, you can check it with the video that I'll have here in a little bit, and I also left the sheet so you can check with the sub to have that also. Okay, now, so this was number 1. As you look at this, this had 3 sign changes for the regular function, so there was a maximum of 3 positive, or if we take a pair away from that, that could go down to 1. When we look at f of negative x, okay, when it simplifies out, you should have a positive, 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 positive. So there are no sign changes at all. I kind of like when this happens because this tells you don't worry about finding any negative zeros at all. There are none. It doesn't happen. When you look at this, you have an x squared even for your last term here. So all of these have an x squared or more, so that can be taken out and factored out front. And that tells me that I have 2 zeros where I would have an x squared factored out front. So x equals 0 once, and then x equals 0 again for the x squared. All right. With that being said, okay, because it has a power of 5, the lowest even number underneath 5 would be 4. So it's possible it could have 4 imaginary roots as you go with it. But if you kind of look at the table, if we go through 3 positives and no negatives, and our 2 zeros that we have to have here, okay, that gets me to my total of 5. The other option would be if I had 1 positive, I still have to have 0 negatives. I can have my 2 zeros that I'm going to have with this. All right, those have to happen in there. Well, then I'm going to have 2 imaginary there. As I play around with this, the reason why they have the 4 crossed off is because I have to have 3 or 1 positives. I can't have any negatives, so that has to be zeros. And I have to have 2 zeros that work in here. So there's no way of getting to 4 imaginaries on this. For problem number 2, we have 3 sign changes for the regular f of x function. So there could be 3 or 1 positives. When I look at p of negative x, I have 1 sign change between the last 2 terms here. So I could have 1 negative. With that being said, I could have 3, 1, 0, and we have 0 for this because there's a constant term. We can't factor any x's out. So then I would end up with 0 for this here. Then I could go down to having just 1 positive. I'd have to have the 1 negative. I have 0 for this, and then I have the 2 here to make my total. 3 here, you can see that we have 2 sign changes, so I could have 2 or 0 positive. I have 1 sign change for my q of negative x, so I have to have 1 negative. I have 0 zeros because I don't have an x that could be factored out because I have a constant term. So when I play around with this, in total, in order to get my total of 3 here, I could have 2 positive, 1 negative, and then 0 and 0. Or I could have 0 positive, 1 negative, and 2 imaginary, kind of replacing the 2 that we took away there. If you take and you graph these, I forgot to do this on the other ones, but the bottom one is the correct one here. The bottom one was the correct one here, and back over here, the bottom one here was the correct one. So make sure you're checking those with your graphic calculator to see what's happening. On number 4, I have 1 sign change here from the positive to the negative. When I do f of negative x, I have 1 sign change from my x cubed to my x squared. And on this, I can factor out an x, so I'm going to have 1, 0 there. So the max I can have for positive is 1, the max I can have for negative is 1, and the max I have for 0, I have to have 1 there. Well, because it's an x cubed, and I have to have 1 on all of this, there aren't any imaginary that can happen there to get my total of 3 going across, and that's the only option. So that's pretty much what we're going to have to look for would happen when you look at your graph. For number 5, I have 3 sign changes, so I could either have 3 or 1 positives. When I do g of negative x, I have 1 sign change, so I have to have a negative root. For zeros, there's nothing I can factor out, so the 0 column is going to be 0, and then my highest power is 4, so I could have 4, 2, or 0 for maximum number of imaginaries. So then when I plug it in, I can have 3 for positive, 1 negative. That gives me my 4, so everything else is 0. Or the 3 could go down to a 1. I could have 1 positive. I still have to have my 1 negative, but now I have 2 imaginaries that filled it in. And that would be the correct answer that actually happens when you're looking at this. So you're going to have 1 crossing at positive, 1 crossing at negative, and then you have 2 that you can't see because they're imaginary. They don't cross the x-axis. Looking at our next page here, we are looking at coming up with the equation when they give us the roots. And remember that imaginary roots come in pairs. So when I have this x equals 2i, not only do I have x equals 2i, I also have x equals negative 2i, because they always come in pairs. So those are my roots as I'm going through here. You have x equals negative 1, x equals 2i, and x equals negative 2i, because they always come in pairs. And that'll make my cubic function that we're working with this. Now, they want you to multiply these together to get your equation. So you need to take your roots. And you guys are used to, if you have x equals negative 1, changing that into x equals, or sorry, parentheses around x plus 1. The same thing is going to be true when we plug in 2i. It becomes the opposite and becomes x minus 2i. And then don't forget you have the negative 2i, which becomes x plus 2i. So whatever the sign is on that part, it changes as you plug it in and make it factors. With this now, you want to multiply the 2 that are the same. You multiply them together. And since those 2 are conjugates, which basically means they're the same thing with opposite sides in the middle, remember when that happens that the middle terms cancel out when you go through your foiling or your double distributing. So as I multiply this together, I'm going to get my x squared, a plus 2ix, a negative 2ix, and then for the end here, a negative 2i times a positive 2i will make a negative. 2 times 2 gives me 4, and then I times I gives me an I squared there. These 2 are going to cancel off because one's just a positive 2ix and one's a negative 2ix. And remember, I squared is the same thing as a negative 1. So negative 1 times negative 4 gives me a positive 4 down here. So this whole part here simplifies to x squared plus 4. Then you're going to take and distribute. So to distribute the x through, get x cubed, distribute the x again, get 4 plus, you get plus 4x. And then take the 1 and distribute it and get your x squared. Take the 1 and distribute again and get your 4. Combine, or really in this case, rearrange. So you have your x cubed, your x squared, plus 4x plus 4. For this last problem here, they give me that x equals 1 is a root, and it has a multiplicity of 2. Then they also give me 3 plus I. And remember, the imaginary roots come in pairs, so 3 minus I is also going to be a root. So what type of function is this, and give your reason? Well, since we have a 3 plus I, we're also going to have 3 minus I, plus we have that x equals 1 is a double root, so that gives us a total of 4 roots, making it a quartic. Now multiplying this all together to try to come up with our equation. And they want integral coefficients here. Let me get this to go all the way. Which means they just want integers for the front of it. Okay, this answer that we're going to come up with down here, that's not the only answer that could possibly work. There could be like a 2 multiplied through the whole thing, but this is the simplest version of it that is going to work. So since we had a double root with x equals 1, we have x minus 1 again. That'll cover those. Then we have to do x minus each of our other roots. So it's x minus 3 plus I. And that minus is going to get distributed through the parentheses that you can see in the step down here. It becomes x minus 3 minus I. Same thing with this one here, but now we have the 3 minus I. So one has 3 plus I, one has 3 minus I, and on both of them the negative has to get multiplied through. So then this becomes x minus 3 plus I. The easiest thing to do is to work with the ones that are alike and multiply them together first, okay? So go through multiplying, distributing. So x times x gives me x squared. Then x times negative 1 gives me negative x. Then take this negative 1, distribute it through. So negative x, negative 1 times negative 1 gives me positive 1. So I'm just double distributing, foiling, whatever you want to call it, to get this part here. Combine the negative x's and they get the negative 2 there. Then for working with these two here, you're just distributing through. So I'm going to take this x and I'm going to multiply them through everything in the last parentheses there. So x times x gives me x squared. Then x times negative 3 gives me negative 3x. Then x times the I gives me plus ix. Then we're going to take this negative 3 and multiply him through everything in that last parentheses. So negative 3 times x, negative 3 times negative 3 gives me positive 9, and negative 3 times I gives me minus 3i. Then for these last couple terms, I'm taking negative I and multiplying him through. So I get negative ix, then negative I times negative 3 gives me positive 3i, and negative I times positive I gives me negative I squared here. But remember that I squared is negative 1, so I have a negative times negative 1, which becomes a positive 1 there. Couple things in this here cancel out, which is nice. That's what we really want to happen. Did that again. Okay, we want that to happen. So the positive ix cancels with the negative ix. The negative 3i cancels with positive 3i. And this is changed into a positive 1. And doing that gets rid of all of our imaginaries. So now we're back to an equation that looks like this after we have combined the negative 3x and the negative 3x here, and the positive 9 with the positive 1 to get 10. Now these two equations, once again, we're going to distribute everything through. So take the x squared, distribute it to this one, to here, and to here. That gives me my first 3 terms. Then take the negative 2x, distribute, distribute, distribute. That gives me my next 3 terms. Then take the positive 1, distribute, distribute, distribute. That gives me the last 3 terms. Then combine like terms together. I only have the x to the 4th. I have this negative 6x cubed, and I like to put some kind of marks on them, and it looks like this person's kind of doing the same. Like single underlines, those are my x cubed. So I have the negative 6x cubed and the negative 2. That gives me negative 8x cubed. Then the double underline, those are my squared. So I have 10x squared, 12x squared, and an x squared to give me a total of 23x squared. Then I have a 26x. That's left from my negative 20 here and my negative 6. So it looks like he put a little like kind of triangle underneath it. And then I have my 10 that's left on the bottom. Put them all together and you got your answer. It's complicated, it's kind of long, but hopefully you can follow along. Remember, I'm posting these also as just a PDF so you can look back at them more as you go through it. Work on the day 27 homework and have a good weekend.